You might remember me from 2 of the keynote demos that I done this morning. My job is a cloud developer advocate. So what we understand under the title is basically either a software developer with the license to speak, or how I like to introduce myself as like the bidirectional channel of you developers that build on our platform to the developers inside Google that build this platform. So please feel free to reach out to us. To me personally, you can reach out on Twitter, to me under the name Hossi. And we like to hear your stories, like how you use Google Cloud Platform, where you think it's complicated, and where we could do better. Only with your feedback, we can actually improve our products. Now, today, I'm going to talk a bit about Cloud Spanner. On the one hand, about the history of Cloud Spanner, how we got about it in Google. I will provide some explanations what Cloud Spanner is. I also go down to some architecture level and talk about the technologies and the hardware that we use to actually make that possible, what we can achieve with Cloud Spanner. And at the end, I'm going to do some coding and show you a demo. Now, when I talk about Cloud Spanner and look at the history of it, we have to go back at around 12 years to 2005. Now, Google at that point has been around for a couple of years, and our business was growing massively. So we had our AdWords system on the back of a sharded MySQL system. Now, this MySQL system was sharded on the customer ID, and we had to reshard this system several times. The last time we resharded the system, it took actually several years. And this was not a solution that we could go forward. With the way that we were growing, this was not a sustainable solution. So we needed something that can scale to the point that we needed it. So we needed something that horizontally scales. We had a lot of customers. We were growing quickly. We needed a system which is still strong, consistent, and has like the relational database attributes, like the asset transactions, right? So we were dealing with money, we were dealing with budgets, we had customers, we had partners, we had agencies. So eventual consistency was not an option for us. Now, also, every minute the system was down, we and also our customers were losing money. So we couldn't accept any downtime for the system. We needed a system where we can make changes, where we can make updates, where we can make security patches without any incurred downtime. So prior to Spanner, there was no system that could provide all these qualities. And that's the reason we built it ourselves. Now, if we look at Cloud Spanner compared to what we have internally, you get the same system, the same performance, the same consistency as the internal spanner that we are using. So it's the same site reliability engineers that are watching our systems that are also watching your systems. Now, as mentioned already, we needed asset transactions, we needed global consistency. We actually have the highest standard of the consistency. Our consistency model is external serializability. Now, one important part was also that we wanted to tap into the knowledge and the experience of our developers. We didn't want to put a system in their hand which is completely different to what they have been dealing with all their developer time or developer life. So for us, it was really important that certain semantics are the same as you would think of them in a traditional relational database system. On top of that, we added things like automatic and synchronous replication, so we can span multiple regions, and we can actually span globally in Spanner. And for a regional system, that means that we provide an SLA of 4 nines of availability. So this is about 4 minutes and 38 seconds of downtime that we allow per month. Now, for our multi-regional setups, where you span your database over multiple regions, and I will talk a little bit about what that means, we actually provide an SLA with 5 nines of availability, which boils down to about 26 seconds of allowed downtime per month. Another really important aspect for us when we were building Cloud Spanner was to make it open, to enable customers and developers to adopt it easily. So when we started and when we were working with our early access customers, we were focusing on making it as easy as possible to adopt it. So some of these things are, we are using standard SQL NZ 2011. We actually use this across most of our products, database products within Google. We added things like enterprise features, like encryption, audit logging, identity access management, things like that. We spent quite some time and invested some resources in building out client libraries in major languages, and there are more and more of these client libraries coming up where how to connect automatically to Cloud Spanner. And currently in a read-only version, we also have a GDBC driver for Cloud Spanner, where you can connect your most favorite like BI tools directly to Spanner and use them. Now, how does it compare with, like, one of the things that we always get asked or like compared to is, on the one hand, like the traditional relational database system, and on the other hand, like the NoSQL horizontally scalable database systems. And as you see here, we put up like a small matrix of features that we are comparing here. So if you look at a traditional RDBMS, and you outscale the system, usually what you're going to do is you build like a master replica system where you have your master, like a MySQL master, and then you have a failover instance, and you might have some read replicas to free up your master of read capacity to have more write capacity on your master. Now, if you want to do any kind of maintenance on this, usually what you have to do is to fail over to your failover instance if you do maintenance on your master, for instance, security patches or an update of the version. Now that incurs downtime and loses you money, and it's quite some operational risk that you incur there. On the other hand, if you look at like the NoSQL systems, like if you basically outgrew even a sharded traditional RDBMS, many went to like NoSQL, and we're looking at things like Cassandra or other database systems that are out there in the NoSQL space. But what that meant is basically, yes, you do have tunable consistency, but most of the times what you actually do to get consistency, what still is required in many businesses, is that you build this consistency and transaction logic in your application layer. So you pull up this logic into your application layer, and that makes it quite complex and difficult and risky. So with Cloud Spanner, you basically can move this logic back into the database. And you still have these qualities of a traditional database system of ACID transactions with the scalability of a NoSQL system. So typical workloads that we're seeing, especially with our early access program members, can be put in like 4 categories. So the first one is if you have like a transactional system, think of like an inventory management or financial transactions or something like that, and you basically outgrow the size what your traditional database system can handle, then that is like where Spanner can come in. You still have like the need of transactions, but like your traditional systems can't handle the size of the database, and Spanner can do this for you. Like with the horizontal scalability, we can also scale the data size or the database size. Now, if you look at like one of the things that we get asked often is also like, well, is Cloud Spanner only for big databases? And I have to say no. Like even if you have small databases which are a couple of gigabytes big, but you have a lot of traffic on this database, and you outscale your solutions in terms of read and write transactions that you can run, this is another use case for Cloud Spanner, if you need to scale read and write transactions. Another thing is if you have mission-critical applications. So you really need a database system that is available 4 nines or 5 nines, and you just can't make any sacrifices on this. Again, that is something where Cloud Spanner comes into the play. The way that we architect it enables this high availability and disaster recovery, and enables you to basically build a global data plane, where you can have, for instance, if you think of a supply chain management system and you want to really know like what items are still in your storage and which items you have sold and things like that. You want to be as accurate as possible, and you want to have a view on your data as recent as possible. And the fourth is, if you think of systems where you traditionally ETL data around. So for instance, you have a user base in a MySQL or Postgres database, and then you have like some log data or some audit data in a Cassandra cluster. And then at the end of the day, you ETL that into another system and do some analytics on this. Now, this is, again, also a use case for Cloud Spanner. Since we can scale on read and write as well as on storage, you can combine and have these data co-located in one database and do all the analytics there. So to talk a bit about more the architecture of Cloud Spanner, I want to synchronize on the terminology, so to say. And everything in Cloud Spanner starts with an instance. So the instance is basically where you define how many nodes you want to have for your instance. So what the scale, the horizontal scale of your instance, and the capacity of storage. Now in this instance, you can create a bunch of databases. Currently, the limit is set to 100 databases per instance. And then in these databases, you can create tables. Currently, per database, you can create about 2,048 tables. Now, this is basically what you see as a developer and as a user. To enable us to distribute your data and to distribute and scale on reads and writes, we have another concept underneath, which is the internal concept, which we call split. Now, what is a split? A split is basically, if you look at it as a table and you have your primary key, we divide this table. And we divide that based lexicographically on the primary key. So, or you could say also alphanumeric ordering, or alphabetical ordering, basically. And we basically use ranges and assign these splits to worker nodes. Now, how does that look like? So if you look at an instance view of a spanner instance, you have in a regional instance a distribution over 3 zones. So we have our compute on the top, as you can see. One spanner node means you have one compute node in each zone for a regional instance. So for regional, that means you have 3 compute nodes in 3 zones. And then you have storage in all of those, like assigned to that can be used by these nodes. So now if you want to distribute the reads and writes, you basically take these splits and assign these splits to a set of nodes across these 3 nodes, across these 3 zones. But I mentioned earlier that we are globally consistent. So one of the criteria here that is really, really important is that there's never more than one group of nodes responsible for a split. And we actually need one member in this group who is the leader of this group. And what we are using to do this is, on the one hand, Paxos. So the Paxos algorithms basically allows us to vote for a leader with a majority voting. And we need another thing to make sure that we have exactly one Paxos group and exactly one leader for any split. And what we use there is something that we invented and called true time. Now, what is true time? If you synchronize your watches with your neighbor, and you go away and you come back together in a week, and you look at your watches, it's very highly likely that your watches have drifted. So they drift because of cosmic rays, they drift because of different temperatures that you have been. There are many factors that let your watches drift. Now, to ensure for us that we have exactly one leader, we basically need something that is close to a global wall clock time. And I mentioned our spanner is distributed across the globe, so we need something where we can synchronize time across the globe. Now, it's not possible, as I just mentioned, to just use a watch, synchronize it in one place, and go somewhere and distribute these watches to all our data centers. They will drift away, and they are not synchronized anymore. And then basically what could happen is that you have two leaders for the same split, which means your data can become inconsistent. So what we needed is basically we needed something to quantify the drift that we have between these data centers, and we needed a technology to synchronize all these watches in our data center. So what TrueTime does is actually, it doesn't give you a specific time. TrueTime gives you an interval. So you have a lower bound and an upper bound. Now, the lower bound of your TrueTime timestamps is a timestamp where you know that this timestamp has passed all over the world. So this timestamp that you get as a lower bound has passed. You know that for sure. Now, the upper bound that you get is a timestamp that has passed nowhere in the world. And you can be sure that this is the case. Now, we use this to select the leaders and make sure that we have exactly one leader and one Paxos group for a split. And by that, we can ensure that we have global consistency. Now, how does it look in hardware? We have in all our data centers, we have atomic clocks and GPS receivers, or time clocks, so to say. And we use GPS to synchronize the clocks around the globe. And then we have atomic clocks, which we synchronize with these GPS time masters. And every time we ask for a TrueTime timestamp or interval, we use a subset of our time masters that are available in our data center. And then we get it back, and if there's any outlier, we basically can say, OK, this atomic clock is bad. We don't care about this anymore, and we use the ones that are looking more reasonable. Now, we synchronize these clocks. We describe it in our paper like roughly every 30 seconds. And as you can see there, the clock drift is about 200 microseconds per second. And so the interval that you get can get down to like single digit, like very low single digit milliseconds. So that basically means all over the world, we can get an interval where we know like the lower timestamp and the upper timestamp are not further away than 2 milliseconds or maybe 1 millisecond. And we know that the lower bound has passed everywhere and the upper bound has passed nowhere. And this enables us to do this global consistency. Now, some of you might ask, what happened if like all my atomic clocks fail in a data center, or all my time masters fail in a data center? Now, we can still get these true timestamps or timestamp intervals from a different data center. And we calculate like all the time of the transmission and things like that. What basically means this interval becomes bigger. Maybe this interval is then 10 milliseconds or 100 milliseconds, which basically means, yes, our database system is slowing down, but it's not stopping. We can still operate. We just slow down a bit. And that, I think, is pretty amazing. Now, let's have a look at a more practical example. And I like to explain that based on the life of a query. So in this case, I'm selecting all events where the name is Cloud Summit Paris. So think of like the agenda that we get back for this. Now, the client sends the request. And in our case here, it comes into one of our followers in this Paxos group. So we have a leader in zone 2, and we have 2 followers in zone 3 and zone 1. Now, the request comes in through the follower in zone 1. And that one will basically ask the leader and say, hey, do I have the most recent data? Like, I am seeing this timestamp of the data that is requested. Is this the latest timestamp that you have? Now, if the leader says, like, yep, you're current, I can just serve that data from a follower, and I'm done. Now, in the case that my request comes in and my follower, so my replica in this case, doesn't have the data, the leader will respond and say, like, no, you don't have the most current data, but just wait. The data is already in flight. So just wait out that time till you have this timestamp of your data. And once you see that timestamp, you can serve the data, because then you know for sure that you have the most current data. So I basically just wait, and then I send the response to my client. Now, another really powerful feature in Spanner is that you can do consistent stale reads. Now, what does that mean? A consistent stale read basically means that you provide a boundary or you provide a specific timestamp within 7 days, where you say, I want to see the state of the database on that specific timestamp. Or I want to see the state of the database, and I don't care if it's up to, let's say, 15 seconds old. Now, so basically, in this case, I'm sending a request from my client. It comes in again to one of the replicas. And I say, it's fine if this data is 15 seconds old. If that is basically the data in most of the cases, like in the most of the cases, this data will be already at the replica. And they will have a timestamp where they know, OK, they can serve this data, which is within this boundary of 15 seconds staleness. And they can just respond to the client. We don't have to ask the leader or anything. And this is especially powerful if you have a Cloud Spanner instance that is globally distributed. That is, you have, let's say, a read-write master setup or read-write quorum in the US, and then you have read replicas in Europe and in Asia. Now, if you have Asian clients coming in, and they don't care if they have the most current data, but they want to have a consistent state of data, they can be served with data immediately from the read replicas in Asia without consulting the read-write quorum in the US. And that speeds up your queries quite a bit. Now, if we look at the read-write transaction, you can imagine in a read-write transaction, I need the leader involved. I'm changing the state, and I'm globally consistent, so I need the leader to be involved. So in this case, we are routing the request directly to the leader of the Paxos groups that are involved. So if multiple Paxos groups are involved, we use two-phase commit to basically communicate and synchronize between them. If a single Paxos group is involved, we basically can just do the transaction within this Paxos group. Now, in my example here, I'm reading, I want to update my talk, as you can see here. So the first thing that I do is I do a read. I get my query result and already acquiring some logs. And then I'm doing some changes. I'm writing this basically this mutation to a buffer, and then I'm committing this transaction. And the leader basically at that time sends out the write requests of this new data to the followers or the replicas. And as soon as a quorum, so the majority of that Paxos group, responds with, yes, I have written that data, we basically can respond to the client and say, like, your transaction has been successful, and we can release the logs. Now, as for the data format or the layout, like what we have in Spanner is exactly what you're, like pretty much what you're used to from a traditional database system. So we have tables with columns that are strongly typed. As you can see here as an example, I have a singles table and an albums table, and I want to join them, for instance, by the primary key. In this case, I'm using the singer ID as an example. Now, in traditional database systems, you have something like a foreign key constraint, where you can say, OK, if I delete a singer, I want to have all my albums deleted as well. Now, in a distributed system, this becomes really complicated and very harmful. So we don't support this semantic. But we support a little bit like a foreign key constraint minus minus semantic. So in case you have something, we have tables that you join a lot, and where you want to be sure that this data in these tables is co-located, we have a construct that is called interleave tables. So in interleave tables, what happens is basically you interleave your child table into a parent table based on the primary key. So the child table has to basically be preclude with the primary key of the parent table. And then we basically can interleave this data right where the parent rows are living. So basically what happens is they end up in the same split. And as you know, like the split is managed by one compute, so or one Paxos group, so we don't have to go to like different compute nodes and get all the data together if we do this join every time. Now, you have to be a bit careful about this. Don't overuse interleaving, Because, as just mentioned, it all ends up in one split, so you can run into things like hotspotting, or you can exhaust actually the storage limits of a split. So you have to be a bit careful there. Now, what does it look like in SQL or in a DDL statement? You basically just add like the interleave in singers, or interleave in the parent table, and then you can actually have multiple levels of this interleaving if you need to. Another powerful feature that I mentioned earlier is online schema updates. So if you want to evolve your application and you want to add columns or things like that, you can do that while all your load is going on. And it is done in a transaction. So they are transactional consistent if you do a schema update. For instance, here, if I'm changing my singles table and add a column H, I can do that inside a transaction. So there are a couple of schema design don'ts, which are coming from the nature of this being a distributed, horizontal, scalable database. So if you come from a MySQL or Postgres world, this is not a lift and shift that you can do. You can't take your application that you've built on top of MySQL or Postgres and just move it over. You have to do some redesigning and some changes on your schema in most of the cases. So one of the things that are really harmful in Spanner are things like an auto-increment integer. So think of like auto-increment feature in MySQL, where like every time I insert a row, it gets automatically assigned a new ID. Now, if we have like these, we have monotonically increasing numbers. And as I mentioned earlier, we are doing splits by alphabetically ranges, alphabetically sorted ranges, or lexicographic ranges. Now, you can imagine if you have a monotonic increasing ID, or timestamps, for instance, every time you insert data, it basically gets inserted into your last split. And you're hotspotting on your last split. Even though you might have 1,000 splits for your table, and you always insert a row with the most current timestamp, you're basically sending all this data to the last split. And by that, you restrict your scalability, and you hotspot on that split. Again, also, with interleaving, the same problem, like if you interleave a lot of data into one row, into one parent row, you interleave all this data into one split. And again, you can also cause hotspotting. So be careful with how deep you go and like how much data you interleave into a parent table. So just to give an example, this is a little bit more graphically here. If you have a timestamp as a primary key, like a last success timestamp, for instance, and then user ID and some other data for each of your rows, since it's lexicographically ordered, you get all these into one split. So what can you do to avoid this hotspotting? So one of the things that you can do is using UIDs, and their preferable version 4 or later as their primary keys. You can do things like that you add a sharding counter or sharding ID to your data in front, like you add a sharding ID to your timestamp and things like that. So as an example here, again, same table as we saw before. We have our last success timestamp, we have our user ID, and we just add in front of it a sharding ID. And by adding this sharding ID, now we can actually distribute the load of inserts or updates on these rows across multiple splits, and you're not hotspotting on a split. So with this, I hope you got some insights on like how Cloud Spanner works under the hood and what things to pay attention to. And now I want to show a little bit demo and want to show a little bit like how you can get started with Cloud Spanner. So please switch to the demo laptop. OK, perfect. So your first stop is Cloud Spanner or cloud.google.com/spanner, which is basically your intro page into Cloud Spanner, and has a multitude of information linked from there. I want to point out a couple of things, or like actually one thing down here. There have been a couple of case studies with our early access members for Cloud Spanner. And one of them is Quizlet, that moved from a sharded MySQL system to Cloud Spanner. And they talk in like very technical and very detailed about their transition from sharded MySQL system to Cloud Spanner. So if you are in the situation that you have a sharded system and you want to explore Cloud Spanner, this is a good start to look into like what are the things to pay attention to. Another thing that we sometimes get asked is, does Cloud Spanner defeat the CAP theorem? Now, like if you look at distributed systems and you know like Eric Brewer, he like came up with this CAP theorem where you have to basically choose 2 out of 3 of consistency, availability, and partitioning. So like you can't have a consistent available system that is also partitioned, right? Things like that. And now some ask like, okay, does Spanner actually defeat the CAP theorem? And the answer is no. Like if Cloud Spanner becomes partitioned to the thing that we don't have a majority anymore for our Paxos groups, we default to a consistent system and become unavailable. But the likelihood is very, very, very low. Otherwise, we wouldn't give out an SLA of 4 nines for regional or 5 nines for multi-regional. Because of the system and the hardware that we have underneath and the way the spanner was architectured, this likelihood of a split brain, how it's called sometimes, is very, very low. Now, another thing that I want to point out is if you look into building a new application or like migrating an application, please read our white papers that we have linked in the documentation, which talks a lot about do's and don'ts in terms of schema design and query design. There are some specifics to Cloud Spanner to get the most out of it, and we want to enable you to get the most out of it. So for the ones that have seen the keynote demo this morning, you already know how to create a Spanner instance. I just want to show that really quickly again. This is basically the home screen if you've created a project in the Cloud Console. So let me actually pump this up a little bit. So if you want to go to Spanner, you have multiple options. To go to Spanner, you either can use the hamburger symbol here on the left and look for Cloud Spanner. You can type into this field up here in the search. Or if you're a Vim user, you know how to search in Vim. Basically use slash, and automatically focuses into the search box, and then you can do Spanner and click on it, and you're in Spanner. Now, to create an instance, I just click on create an instance, I name it, I select a configuration, let's do Europe, and I say like 5 nodes, and I create. And as seen in the architectural overview that I've shown, no, I have no sufficient quota. Let's do 1, and fingers crossed that it works. So as we've seen in the architectural diagram, we are actually distributing and separating the compute and storage to enable the horizontal scalability. Now, to create a database, we do the same thing. Like I say I want to have a demo database. I can use our dialogues to create a schema. For instance, if I want to have a singles table, I create a singles table. I'm adding a column, for instance, age. I do int. I have to select the primary key, and then I click create. And again, within a couple of seconds, you have your database. Now, just to show you, if I want to edit this, I can do an edit schema. Again, I can use DDL or our dialog, and I can say, for instance, city, and I'm adding string, and do the done, and then save. And as you will see in a second, there's a box coming up which shows that this is basically running in a transaction, the schema update. So as soon as this transaction has finished, the new schema will be available. Now, I want to switch a little bit to more like complex schema. And again, you might remember that one from the keynote demo. I basically have the scenario of a ticket broker where you have event organizers that want to sell tickets, and then you have customers or fans that want to buy tickets. And I just came up with like a sample application to represent such a system. Now, what you have in this is, on the one hand, for instance, if you want to have tours, like a Bruce Springsteen tour, Sting tour, or whatever, Coldplay, you have a multi-event, which includes basically multiple events in different cities. Then you have the events. For each event, we need a venue. So you see a venue up there as well. And then each of these venues has different seating categories and configuration. So you can, for instance, have general admission, You can have premium seating, you can have VIP, and all these have different prices assigned. So it gets, like, if you think about it, like complex quite quickly. Now, I did one thing here, as you can see, I interleaved the venue into the seating category actually into the venue. Because I'm doing this join very often, so I wanted to have actually the seating category co-located with my venues. So I used the interleaving in this case. All the other things are basically standalone tables, and I can join them by IDs as I wish. So the first thing that I want to do is, and then in my case here, I'm using Java, is to show you how to get started with Java and connecting against Cloud Spanner. Now, just to check, how many Java developers do we have here in the room? OK. How many Go developers? All right, so you, the cool kids on the block. Python? Oh, wow, I should have done a Python demo. All right, next time. So in this case, I hope you bear with me, Python and Go folks, that hopefully you can read my Java code. So the first thing that we want to do is we want to authenticate. Now, if you run this on your local machine and have that set up with the gcloud SDK, or you run it on any of our GCE instances or inside Kubernetes, you get a default authentication context on these machines, and you can just use this. So this is really easy. I'm just saying Google credentials.getApplication default, and I'm authenticated. So I think this is amazing. Just imagine like what you would have to do with all kinds of things, of keys and OAuths. Yeah, it gets messy, and I wouldn't be able to do this in the time that I have left. Now, in case you need to authenticate with a key, we also have the possibility that you create a JSON key, like a service account, and then you use that to authenticate against Cloud Spanner. Now, the next thing is I need a client stub. So I need to say which instance am I going to talking to, which database am I going to talking to, and use all this information, like the project ID and things like that come from this authentication context. And then I create a database client. So as you can see here, I'm creating my client. The next thing is what I want to do is, in this case, is a read-only transaction. So the read-only transaction, the advantage of this is I don't need to acquire any logs. So I can just do this. So I want to have a read-only transaction. And you basically what you do is db client.single-use read-only transaction in our case. And then I want to, of course, run a query. So here, in this case, I'm looking for all my multi-events that are happening from right now till tomorrow, so 24 hours later. So as you can see here, I'm using a statement builder, and I can put parameter placeholders and then bind these parameters down here, as you can see. So I'm using basically for the date timestamp now, and then for the next day, I'm creating a new timestamp where I'm adding 24 hours. And last but not least, I, of course, want to show this and iterate through my result set. So I basically just, like, as we know from iteratable, we just iterate through the list till we don't have any result sets left. And I can point to the results in from my query either by location, so ID. In this case, like you see, get string I0, which basically means I want to have the first position of my query. Or you can also use the column names if you use them. So I could use basically multi-event ID, for instance, as to get the value of this for this row, for this column. And then I can run all this. And fingers crossed, it hopefully works. So you see, I also limited it to 10 results. So we see that it runs. Now, this took a little bit. And that is because like creating the connection to Cloud Spanner takes a little bit of time. If I would run it like multiple times with the connection standing, it gets much, much faster. So you get to single-digit query response times, actually. Now, I mentioned that we can do stale, consistent reads. And what I can do is I just modify my single read-only transaction. And I'm adding time bound. So as you can see up there, I'm adding a timestamp bound of a max staleness of 15 seconds. And by that, basically, if I come in through a follower or a replica, the replica can respond with the data right away. So we can just run this again, and you will see that we get some data back as well. Now, the next thing that I want to show is a read-only transaction. Now, I have all this stuff here already, so this is just a repetition. So I'm going to jump right away to the insert transaction. Now, what I do here is a write-only transaction. And first of all, what I have to create is a mutation. So we don't have currently DML. You can't do like insert, into, and things like that. But you can use the client libraries, and they have an idiomatic way of inserting data. Now, there's something that we use is called mutations, and I want to elaborate a little bit on this. In Spanner, a mutation is basically a change of a cell, like a modification of a cell. So that means if you have a table with 5 columns and you insert a row, you have 5 mutations. Now, why do I mention that? The thing is, for a transaction, we have a limit of 20,000 mutations per transaction. And you have to be aware of this if you are adding indexes on your table. For instance, we have our 5-column table, and we add an index with 3 columns, where we do an index on 3 of the 5 columns. Then we basically have, for each row that we add in our table, we have 8 mutations, 5 for the table and 3 for the index. And that's really, really important to remember if you ever see that error like exceeding mutations limit, that you think of like, okay, a mutation is not 1 row, 1 mutation. A mutation is 1 row multiplied by columns, and so on, and so on. So in this case, I'm creating an account. I'm adding like my name, like email address, and everything. And then I run this. There's one thing that I want to mention. Yeah, basically, yeah, here you see I'm basically doing db client.write, and I provide these mutations, and I'm just running that. So this will return me with a timestamp when this has been written. Now, we have this in the database, and I can show that really quick. I have here my demo instance, and I'm going to go to the accounts, and if we go to data, we're going to see here my data that just got inserted. Now, one of the things that I want to do is, if I want to do a read-write, right? So I have to create like a transaction context in my client, and then do the read, which I can do either through the read API or I can use SQL. So in this case, I'm creating this read here, and then my mutation. But there's something special about this construct. As you can see here, we do this read-write transaction, and we provide a transaction runner transaction callable. Now, why are we doing this? As you can see here, we basically provide the client library a complete function of this transaction. And that enables us from the client side to rerun your transaction in case it fails. So you basically provide us all what has to be done in this transaction, and we can rerun it on the client side if there should be any problems with this. So again, if we run this, I'm just basically selecting my account, and I'm changing my name from Robert to Spanner Guru. So if we go back here and go to our account table, to my data, we now see that my name has changed. And then I could do this also programmatically, but we just recently added this feature in our Cloud Console that you can now also edit data right here or delete it. In my case, I want to clean up after myself, and so I delete this data. This is back to the slides. So with 1 minute left, I just want to mention like briefly the other database products that we have in our cloud platform portfolio. So our database products range from in-memory databases to like the data warehouse databases. So if you, for instance, build on App Engine, you can use our App Engine Memcache. If you look at a relational, we have a managed database service where you can have MySQL or Postgres as a managed solution, which can be set up with failover and read replicas. But that is a vertical scalable solution. Now, if you need horizontal scalable solution for the criteria that I mentioned throughout this talk, you're looking at Cloud Spanner. If you look at like more the NoSQL databases, we have two offerings. One on the one hand, Cloud Data Store, which is more like a document store, and then we have Cloud Bigtable, which is a key value store, which can have like a immense throughput and scale with your needs on the throughput side and also on the query side in terms of like single-digit query response times, even if you have terabytes of data in your database. Now, Cloud Data Store supports you from small applications up to huge applications. Just think like Snapchat built their entire application on Data Store and App Engine. And then if you look more onto like object solutions, you can look into cloud storage where you can save basically blobs, like video files, anything. The nice thing about cloud storage is also it's backed by Spanner again, and it enables you to, if you store a file and you look anywhere in the world on the state of like what kind of files you have in your buckets, you will see a consistent state across the globe. So if your data is there, you will see it from everywhere, and that's enabled by Cloud Spanner. Now, if you want to do analytics, we have a like cloud-native solution, like fully managed solution called BigQuery. And BigQuery is amazing to crunch through terabytes, even petabytes of data in seconds or very low minutes. So if you're looking at like lowering your costs of ownership in doing analytics, BigQuery is one of your things where you should look into. With this, thank you very much. I hope you enjoyed this talk and enjoy the rest of the day.